In Toronto, this is 94.1 CBC Stereo.
There will be a Voyager report in 30 seconds.
Before we start, you might want to note down our address. It's Ideas, CBC Box 500, Station A, Toronto, M5W1E6. We have a free color poster of photographs of Saturn, and we'd be happy to send you a copy. Our address again, Ideas, Box 500, Station A, Toronto, M5W1E6.
We're just not smart enough to predict nature. We need measurements.
If you can't make measurements yourself, these days you can send a robot to do it for you. NASA sent a robot to the ringed planet. Tonight, on Ideas, Voyager at Saturn, a radio documentary from the Voyager Control Center in Pasadena, California, prepared and presented by Ideas reporter John Lomberg.
Saturn is nearly 1 billion miles away. Even in the most powerful telescopes, its moons are no more than tiny specks. The Saturn system was the final planetary visit for the Voyager 1 spacecraft, which swept past Jupiter in March 1979 and reached Saturn in November 1980. The spacecraft discovered intricate fine structures and mysterious dark spokes in the rings. It observed features in Saturn's atmosphere reminiscent of the clouds of Jupiter, but also discovered some strange differences between the two planets. And it photographed many of Saturn's known moons and discovered some new ones. Voyager's trajectory brought it close to the cloud tops of Titan, a giant moon bigger than the planet Mercury, and discovered that Titan may be the most interesting place in the solar system to visit again. These discoveries were crammed into a week of intense activity at the Jet Propulsion Laboratory in California, Voyager's control center. Tonight, you'll hear what it was like during that week as the scientific teams moved from mystification to understanding during the close encounters with Titan and Saturn. As Voyager cruised toward Saturn, one of its many instruments recorded the sounds a radio would pick up as it crossed the magnetic fields and charged particles that surround the planet. Dr. Fred Scarf.
What we do is very simple. We have some antennas out there, and we just measure the voltage across these antennas many times, about 30,000 times per second. And so if there is a fluctuation in the voltage in the audio range, we can hear it when we record these fluctuations. The two kinds of waves that are detected this way are either very low frequency radio waves that are not ordinarily thought of as sound waves, or things that are much more like sound waves, compressions, vibrations in the charged particles that propagate through the medium just as a compression wave propagates through the air. And this is known as a plasma type of acoustic wave.
Astronomer Brad Smith, leader of the imaging team in charge of Voyager's cameras.
Our pre-Voyager knowledge of Saturn is poor. Much of what we will be seeing or are seeing now is new. And I think we can predict that much of what we thought we understood will be found to be wrong. Now, Saturn itself is a giant planet. One of the investigations of this Jupiter-Saturn mission has been comparative planetology. Both of these bodies have internal heat sources that are greater than the solar energy that is absorbed in their atmospheres, and they therefore tend to have convective type atmospheres which are different from those of the terrestrial planets, Earth, Mars, Venus. We developed theories for what we saw, and are still developing theories for what we saw on Jupiter. And of course, the question now is, will those theories hold up for Saturn?
By Thursday, November 6th, 6 days before a close encounter, the spacecraft was busy making constant observations, and the first fuzzy images of the moons began to come in. Ed Stone, Chief Voyager Scientist.
We have one set of ring images a day, these 6 images on the rings with a resolution about 100 miles per line pair, 160 kilometers per line pair. There are satellite searches going on late tonight, which are just out, images taken just outside the edge of the A ring. That's done twice during the night. In addition, today we have every 6 hours images of Titan coming in. They're in your timeline. So every 6 hours we're imaging Titan.
We have
infrared data on the planet.
photographs of Titan now, which is the most extraordinary place.
Carl
The
Sagan.
largest moon of Saturn, and it has by far the densest atmosphere of any moon, and in fact of all the small bodies in the solar system, it has the 3rd densest atmosphere after Venus and the Earth. We also know that it is swaddled in reddish-brown clouds, and the prevailing hypothesis is that those clouds are composed of complex organic molecules produced by probably ultraviolet light from the sun, from the methane in the atmosphere, and so is a world repository of complex organic molecules that have been building up for long periods of time, and because the surface temperature is probably quite low, are not being destroyed at high rates.
We don't know how much atmospheric pressure there is on the surface. It could be as little as 2% of that of the Earth, or twice that of the Earth. If it's a very dense atmosphere, 2 atmospheres, in fact, one might even imagine having liquid nitrogen lakes on the surface.
There are, today, pictures beginning to come through showing faint disks with feeble dark markings on them of moons, worlds, which some of them have never had a scientific paper written on them. And now we're beginning to see the markings on them. We now can see Dione and Tethys and Mimas. There's a lovely picture that came in today of Mimas and the F ring.
David Morrison.
It seems as though all of the satellites inside of the orbit of Titan form a regular system of roughly similar objects. These are the ones that we know to be ice-covered. What information we have, which is so far sketchy, suggests that they are low density, which would mean that they were ice all the way through. And they're in this size range from the largest, Rhea, about 1,500 or 1,600 kilometers in diameter, down to these little ones that we're discovering right and left along the edge of the rings, which may all be part of a continuum of icy bodies, going down from the very small ones up to the largest.
And perhaps even including the ring particles at the far extreme of this whole spectrum of size.
Philip Morrison.
I think of everything that has ever been revealed by the telescope, the most significant to most people is the ring of Saturn. I mean, it's the only one you put in a cartoon, immediately recognizable as to what it is. It is a 2-dimensional structure. It's all surface and no volume, but there it is, and it's been our cynosure and the mark of scientific investigation of the universe ever since its discovery. And it was none other than Maxwell, then a young graduate student in the 19th century, who first showed the dynamics told us, physics told us, that the ring of Saturn could not be a flat disk spinning in space. That was only the eye's version of the ring, as the eye's version of electric fan blade is a ring. But it's not, it's just loose particles orbiting separately, whose size and nature we will learn, I hope, on Wednesday afternoon or something like that.
DE, in order of their discovery, the A ring being the outermost one, visible from Earth. In 1979, the Pioneer spacecraft had discovered the F ring, a single thin ring beyond the outer edge of the A ring. Astronomers thought that the rings were smooth and featureless, but even a week before the Saturn encounter, Voyager 1 had shown that this wasn't correct. Brad Smith.
sometime quite early in October, I believe it was, we noticed that, very much to our surprise, that there were these finger-like projections sticking out across ring B. Now that does create a problem because you see all of these particles in the rings are like individual satellites, each in their own individual orbit. The inner particles are moving around Saturn with a period which is considerably shorter than the outer ones. And the difference in that period, for example, between the inner edge of ring B and the outer edge of ring B is about 3.5 hours. That's 3.5 hours out of, say, roughly something like 10. Yet these dark finger-like projections seem to extend over enormous radial distances. Now, we think that the shear that one would expect as the inner parts are moving more rapidly than the outer parts would tend to make these features tear apart. And there's some evidence that that happens, but there's also evidence that they seem to fade away by themselves before the shear has the opportunity to disrupt them. And how do they form in the first place? How do all these particles just happen to know that they should turn dark, all lined up, over distances which are tens of thousands of kilometers? Well, the answer to all of this is that we don't know. We do not have a model for these features. It is quite clearly the most baffling surprise that we've come up with yet in this mission.
From Earth, the rings seem to be separated by empty gaps between them. The largest gap is called the Cassini division. It was thought that these gaps were caused by a gravitational interaction called a resonance between ring particles and the moons of Saturn, which orbit beyond the rings but in the same plane. Reality turned out to be more complicated.
There are some places bright ringlets with no dark bands on either side of them. Sometimes there do seem to be dark boundaries. There's an enormous amount of structure in there. And that presents some very serious problems for one of our time-honored theories about what causes structure in the rings of Saturn. We run into even more difficulty when we look at the Cassini division itself, once thought to be empty. In fact, I believe Pioneer actually thought about flying through. Of course, the mission would have ended right about there. And when you look at the structure that's inside just the Cassini division alone, and all of this structure, I think we have to admit that the whole question about satellite resonances forming this structure in the rings of Saturn is not going to work any longer, and we are forced to look for some alternative explanation.
"5 days before close encounter, details in the banded clouds of Saturn itself became visible.
As one looks up into the higher Saturnian northern latitudes, one begins to see more and more features which are very similar morphologically to what we see or did see in the atmosphere of Jupiter. This wave phenomenon, the little small convective cells at the higher latitudes.
A red spot like Jupiter's is even discovered, but so are some differences between Jupiter and Saturn.
What I want to point out, in addition to this complexity of belts and zones, is this red spot. As far as its size is concerned, it's roughly 10, 12, perhaps 13,000 kilometers long from one end to the other, and that makes it about the same size as the white ovals that were observed in Jupiter's southern hemisphere. On the other hand, on Jupiter, the highest zonal velocities, these easterly and westerly winds, occurred along the edge of the belts and zones. But on Saturn, we don't have that situation. In fact, the velocity relative to the deep interior of Saturn along this boundary is almost zero. And what we have in the center of this belt, where on Jupiter the velocities were the lowest, is a fairly strong air movement or wind movement toward the west of the order of, let me check the notes, about 20 meters per second. Exactly the opposite of what we see in Jupiter's atmosphere.
We thought we had a nice explanation whereby upwelling and downwelling zones at different latitudes, coupled with the effects of the Coriolis force, led to currents either flowing eastward or westward at the edges of these upwelling or downwelling zones. And the upwelling and downwelling zones were apparently correlated with the light and dark markings. But apparently this whole relationship has shifted by about 90 degrees from Jupiter to Saturn. And right now we have no clue as to what the difference is.
"4 days before close encounter.
Good afternoon. At 1:30, Voyager is 4,300,000 kilometers from Saturn and approaching it at 56,600 kilometers an hour.
There is now still another feature in the Cassini division. It's getting sort of hard to tell where the Cassini division begins and ends anymore. So we're looking forward with some interest to our very high-resolution photography in the Cassini division. It wouldn't be at all surprising to see all of this breakdown into even more complex structures.
And the other major activity we have scheduled during the next 24 hours, we're spending 12 hours doing this, in fact, roughly 12 hours, is generating a map, and we'll pick our way across the planet, and we'll start again, and we'll continue to do this. This will allow us to measure the temperature as a function of latitude, if you like, in the Saturnian atmosphere. And, well, because of the resolution which IRIS, the infrared instrument, now has, will allow them to separate out the effects of the planet in terms of thermal radiation from those of the rings to more accurately determine the amount of radiation, amount of energy being radiated by the planet.
Here we're seeing very intense wave activity at Saturn.
Meanwhile, Fred Scarf's plasma wave detector was hearing the signals of radio waves trapped in Saturn's magnetic fields, perhaps the signals of lightning discharges in the atmosphere.
Now, one of the things we had been planning to search for all the way in was the trapped radio waves that presumably bounce off the magnetosheath and the plasma sheet. And they're trapped inside the magnetosphere of Saturn, just as the waves are trapped inside of a microwave oven by its metal walls.
2 days before the Saturn flyby, there was another surprise. Study of the ringlets showed that some of them were eccentric, that is, off-center relative to all the other ringlets.
The mystery of the rings, the structure, the mechanism that governs this structure keeps getting deeper and deeper to the point now where we feel that it's like a bottomless pit. We have imagined all sorts of things that we might see in the rings, including maybe even little satellites. I guess the thing that I, anyway, least imagined to find were eccentric rings within the ring system, and we have not just one, but two eccentric rings. As with almost everything else that we're finding in the rings, we really don't have an explanation for this.
The day before Saturn encounter, Voyager made its close flyby of Titan. The big question, what was the atmosphere made of, and how thick was it? Al Hibbs of Voyager Operations.
Good morning at 9 a.m. this morning. The Voyager is 1,890,612 kilometers from the surface of Saturn, and it's approaching it at 59,036 kilometers per hour. It's also 872,000 kilometers away from Titan, and approaching it at about the same speed. And of course, that's the big event of today, the close passage of Titan and the occultation as we go behind Titan and lose the radio signal for that time period.
We're looking at an atmosphere But it's a very different atmosphere than what we see on Jupiter and Saturn. What we're undoubtedly looking at is a very high level haze of particles, perhaps a photochemical smog, which is reducing the contrast of anything that might lie below it.
Von Eshelman of the radio science team.
I would just remind you of the fuzzball that we're dealing with here, where in the visible and even somewhat longer wavelengths, there's no features visible certainly on the surface, and the question of how deep the atmosphere remains an important puzzle. The radio occultation experiment was designed, and the hope was that with these much longer wavelengths, it would be possible to probe below the visible regions and hopefully to find what conditions were like at the surface.
In order to prepare for this particular event, the going behind Titan, the programmers have introduced into the program structure of the computer on board the Voyager something called the movable block. And this is a group of commands to run the spacecraft which can be moved back and forth in time at the very last minute. And the complete block of commands occupies a space of about 2 hours worth of commands on the spacecraft. And it can be shifted back and forth by what is called 4 frame counts, each frame count being about 48 seconds. So that's about 3 minutes. It can be moved one way or the other. Now, the reason for all of this, you recall we had a trajectory correction maneuver last Saturday, and we, of course, could not predict precisely what the outcome of that maneuver could be. We know what we're aiming for, what we're trying for, but there's always a little bit of uncertainty. And to counter that uncertainty, this movable block was introduced so that after we had the results of the trajectory correction maneuver and knew precisely when we were going to go behind Titan, we could then shift this series of commands to match the final orbit, and we could do that at the last minute using the very latest update on the trajectory. Those commands, of course, control how the spacecraft will point its antenna as it goes behind Titan, because the pointing of the antenna determines how deep in the atmosphere we'll be able to see the radio signal coming back to Earth, and therefore how deep we'll measure the characteristics of the atmosphere. And all of the other things, the ultraviolet spectrometer, which has to point at the atmosphere at the time that the sun disappears from view, so it gets the sunlight, the last rays of the sun going through the upper atmosphere of Titan. All of these things have to be quite perfectly timed. And this was the way to do it, since we could not, months ago, when the sequence was originally all worked out, exactly what happens when we could not, at that time, predict exactly when to start it. So now we know when to start it. So we are prepared now. The last steps have been taken to prepare for the Titan encounter and the Titan occultation.
We'll be doing a series of infrared observations. Remember, that's the way we're going to determine the temperature of the atmosphere, and we hope the temperature of the surface. There will be images riding along with those observations, so there will be continuous imaging at better and better resolution. We do the west limb at one time, we do the south pole, and so on, in a very systematic way. And we hope to be able to detect by the thermal emission of the atmosphere right near the limb of Titan off the North Pole. We hope to be able to measure directly with the infrared instrument atmospheric composition.
The Titan occultation was very good. We had a plus or minus 265
But a thunderstorm on Earth endangers reception of the very weak signals radioed back from Voyager 1.
The first encounter of that the Saturn mission, the passage near and behind the satellite Titan has already taken place, and data has been received in spite of the fact that a thunderstorm broke over the Madrid tracking station 5 minutes before the data was due in and lasted throughout the period of that we were so interested in, the period of occultation. Nevertheless, we got the data.
As the radio beam passed through Titan's atmosphere, it was slightly bent. By carefully measuring this deflection, scientists could deduce properties of the atmosphere.
The spacecraft was behind Titan for about 12 minutes. On entry occultation at this point, we arranged to have the antenna beam bent 0.11 degrees to the left in order to handle the bending of the radio rays around the limb of Titan. We then swung the antenna 23 20 times further off in the other direction in order to attempt to probe the atmosphere as deeply as possible. The great power of the radio occultation technique for the measurement of atmospheres has to do in its high precision of measurement. While this spacecraft is 1 billion miles away, when that bending causes a path length difference of an inch, that's easily detectable.
I think there's no question that there's a direct identification of molecular nitrogen in top of Titan's atmosphere.
We have seen Titan in the infrared. As we approached it, the chances are pretty good that the clouds which stop our infrared probing are indeed droplets of liquid nitrogen. And that means that CH4 can only be a minor constituent in the atmosphere, and it must be less than 1%.
This was a totally unexpected finding. Titan's atmosphere is not mostly methane, CH4, as had been thought. Like the Earth, its atmosphere is mostly nitrogen, with more complex hydrocarbons present, compounds like kerosene, perhaps. Even more complicated organic molecules like hydrogen cyanide, HCN, are also present. Hydrogen cyanide is a highly reactive compound that can produce adenine, one of the bases that binds together the double helix of DNA, coding the information of life. Rudy Hanel, who studied Titan in the infrared wavelengths.
It's a very significant molecule because it's the first one which deviates from the simple CH bond and has been considered a building block of more complex organic molecules. Having said that, I want to call your attention that the temperature in the lower region are indeed close to liquid nitrogen, so one should not expect any living creature there.
The clouds would be liquid nitrogen in very small droplets. There could be a source of N2 at the base. When we look at that fuzzball I showed in the first picture taken by the TV, people get the mental picture of a murky swamp. This is a rather bizarre murky swamp, if that's what it is. The murk is liquid nitrogen, and the swamp is liquid nitrogen.
And the pressure of Titan's atmosphere turned out to be much higher than expected. The day after the Titan flyby, Ed Stone announced,
"The first look suggests, certainly, that the thin model of the atmosphere of Titan is not correct, that it must be denser than the 20 millibar atmospheric surface pressure model. How much denser, we do not know. I hope by tomorrow we will know."
Mission planner Gentry Lee.
Now, you've got to remember that the consensus among the scientists 3 days ago was that the surface pressure of Titan was in the 20 to 40 millibar region, which is almost too low to have any real kind of chemistry going on. And here we are, we're talking about an atmosphere that is at least 40% as dense as the Earth's, and I'll be willing to wager that when it's all done, we're going to say the surface pressure on Titan is just roughly the same as that on Earth, maybe even more.
And the next day, the estimate was being revised upwards.
I would say that the pressure at the surface is on the order of, I'm not saying exactly how much, but on the order of 1 bar. That is the pressure at the surface of the Earth, or more, where the more is open-ended at the present time.
And just a few days later, it was higher still. Tobias Owen.
Now, Voyager hasn't gotten data down to the surface yet, but if we take Eshelman's extrapolation at face value, then it's going to be, it looks as if the surface is going to be very close to three bars.
Titan, by size, is a terrestrial planet. It just happens to be located out where the giant planets are. So Titan may be, under this kind of scenario that I'm trying to describe here, considered perhaps a terrestrial planet in deep freeze.
Titan, I would say, probably has the richest chemical history of any of the planets with the exception of Jupiter and Saturn, and their chemistry is all taking place at very, very high temperature. I think it is the place in the solar system that I would most like to visit.
On Wednesday, November 12th, the day after the Titan flyby, Voyager 1 swept past the inner moons, looped under Saturn's south pole, and came up the other side, taking pictures and measurements all the time. For the hundreds of visitors and scientists at the Voyager Control Center, this was the high point of the mission.
Good afternoon from the Jet Propulsion Laboratory in Pasadena, California, and Voyager operations. Today is the day in which the Voyager 1 spacecraft will make its closest approach to Saturn. We'll fly by there. From the spacecraft point of view, it's 3:45 this afternoon. We, however, will get the signals that it sends at that magic moment an hour and 25 minutes later.
I think it's important to spend 1 second explaining the difference between this encounter and the Jupiter encounter. The Jupiter system is so much larger, the objects are so much larger, that the phase that we're going through of initial exploration and finally study up close occurred over a period of 4 days. That experience is going on over a period of about 12 hours in the Saturnian system.
My name is Jack Williamson. I'm a long-time veteran in the science fiction field. My first story sold in '28. The Jupiter flyby was tremendously exciting. I got a short story out of it at least, and I'm here for the Saturn flyby, just like a kid looking at a new toy.
My name is Don Davis. I'm a space artist, and I'm here to get a hint of what really lies out there that we've been stabbing at in our artwork for so long.
We are now getting in some new, just received image of Mimas.
Oh, look at that.
Topography on the icy satellites is very rare. You know, in the case of Jupiter, they flowed up and filled themselves, and the Europa ones, there were crack fillings, but almost no topography. Here's something that really has topography.
To see revealed for the first time these new details, these moons changing from microscopic, telescopic specks to full worlds with all their detail, pleases and inspires the artists who work in this field just as much as any of the scientists or geologists.
We are looking at sunlight coming through the rings. We are now below the ring plane looking at the unilluminated side. So where we see sunlight, it's because the rings are thin enough that the light can get through, but enough material nevertheless to scatter the light so that there's something to see.
The rings alone could fill pages of a description of their intricacy, their engraving-like fine concentric structure with subtle variations and changes.
I tried counting rings in the Cassini division, and when I got up to a few dozen, I stopped. Now, Rich Terrell, who's a member of our team, also tried a little counting over the whole ring system, and I think he was having or getting tired when he was up in the 300 range or so. I think probably before it's all over, we're going to find that the number of individual ringlets, bright and dark ringlets, is somewhere in the range between 500 and 1,000.
The relationship of the satellites to the rings is, of course, proving extremely interesting. Things like having these two satellites on either side of the F ring, apparently involved in constraining it, and this new 15th satellite just skirting along the edge of the A ring. So the interrelations between rings and satellites seem to be closer and closer because the rings are not flat planes of particles as we had thought. They are more and more concentrated in these thin ribbons. The F ring is the most obvious example, but as we get to higher resolution in the main ring system, we see there it dividing into finer and finer structure. And what holds those little ribbons of material together is a real mystery.
Maybe there is not one mechanism to explain the ring. I mean,
The response in life is never yes or no. It's never I have the answer in one sentence. I think a number of mechanisms play a role together. There is a complex physical processes that we don't understand so well, in fact.
With the discovery of these eccentric rings yesterday, not just one, but two eccentric rings, we thought that perhaps we had seen all that there was to see. But in this strange world of Saturn's rings, the bizarre has become the commonplace, and when we looked at the F ring this morning, this is what we saw. There are two components, two bright components of the F ring, and they appear anyway to be braided. Brad, do you have any idea what causes that braiding? What
I really don't. It boggles the mind that it even exists, and no ideas at all yet.
The Voyager is 1,420,000 kilometers above the cloud tops of Saturn and leaving it at very nearly 1,000 kilometers a minute.
Well, I'm just stunned by the spectacular display of pictures that we've received over the past 24 hours. Extraordinary pictures, and in such quantities that it's hardly been possible to concentrate on a particular picture for more than just a few seconds without being distracted to the next. We spent 3 months closing in on Saturn, seeing it essentially in the same configuration as we approached. But then suddenly, in this short period of time, we did a number of things. We dove down under the rings, we saw the rings from the dark side, we came back up again, and now we were looking back at Saturn in roughly the same direction as the sun, sort of in the same direction as looking back at the sun. And that those changing illumination conditions bring out different phenomena. So that's one of the reasons that there is so much science concentrated in this very, very brief period.
Today, over the last 24 hours, we have seen the satellites, the icy satellites of Saturn, growing from mere names out of mythology to real places.
The day after close encounter.
Then there are the spokes, those things that have been giving us nightmares over the past 3 or 4 weeks, and not dark anymore. Now they're bright. Somewhere, somehow, they're trying to tell us what they are by being dark in the back-scattering direction and being bright in the forward-scattering direction. And one immediately begins to think of small particles, perhaps elevated slightly out of the ring plane, being poor backscatterers and good forward scatterers.
After close encounter, the science teams began going through the wealth of data they had received. Suddenly, there were a half-dozen new worlds to study. Larry Soderblom compares the two innermost moons, Mimas and Enceladus.
Mimas appears heavily cratered, very spherical, shows a surface very lacking in surface coloration and albedo, but heavily saturated surface. But its twin, or a little larger, in fact, is Enceladus. Something has wiped out the ancient cratering record on the surface of Enceladus, and we're going to look at this close up by Voyager 2 next August at much higher resolution.
The reason the smooth surface of Enceladus needs explanation is
one thing that is universal in the solar system seems to be debris flying around that will produce impacts. So unless there is something to destroy craters, as is the case on the Earth with the erosion and the geological activity, or the case on Io with its volcanoes, unless there is some active mechanism to destroy them, they ought to be there.
And Ione, where material had flowed across the surface, making bright streaks.
As we flew in closer, we saw that these things were, in fact, broad stripes that seemed to emanate from a large impact crater that Gene Shoemaker pointed out. You notice in Mimas, Tethys, there are not these large, bright streaks associated with these fractures. The fact that there's stuff that can leak out from the inside on these says that there were internal processes going on of some sort on this body. The fact that stuff is leaking out says that there was leaky stuff on the inside. How's that for scientific deduction?
And Rhea, the largest moon after Titan.
So we have seen the bright terrain on Rhea to be among the most ancient of the planetary surfaces we've seen in the solar system, coupled with Mercury, the Mercury highlands and Callisto. Well, this is what the bright terrain on Rhea looks like. Patches of extremely densely saturated impact surfaces, shoulder-to-shoulder craters. They've been falling on top of one another so many times that they've just battered pre-existing craters over the entire surface.
And Iapetus, the outermost moon.
The basic situation on Iapetus is that one half is bright and ice-covered, and the other half is dark rock. The contrast in brightness between these is greater than the contrast we've seen on any planetary surface. It does look as though Iapetus is an icy object, a gigantic snowball which somehow has gotten dirty on the leading side.
And on it went. Tethys, Hyperion, two new small moons that shared the same orbit, each set of observations revealing something new.
I think we've learned more about Saturn, the Saturn system, within the past week than in the entire span of recorded history.
Even the strange spokes began to make a little sense. Rich Terrell.
We've got a story about the spokes. The spokes do a contrast reversal. We saw these in backscattering as dark features and in forward scattering as bright features. It's sort of a clear indication that the phenomena responsible for this contrast reversal is small particles, preferentially in the spoke regions than regions just adjacent to them. If we have a charging mechanism going on here, and there are various ways we can do this, either depositing electrons from auroral discharges on Saturn or photoionization, various methods, we can, if this phenomena is somehow modulated by Saturn's magnetic field, then we can preferentially raise up clouds of small particles by simple electrostatic repulsion, electrostatic levitation of a cloud of small particles. And we are now converging on this as being the idea behind the visibility of these dark features in the B ring.
There are still many aspects of the dynamics of the rings that we don't understand. Now, there have been statements made that these features are not obeying the laws of physics. Well, of course they're obeying the laws of physics. They are doing exactly what the laws of physics tell them to do. Our problem is in understanding those laws. And particularly in this curious intertwined, interbraided F ring, there are obviously forces acting on these particles that are in those rings other than just pure Keplerian mechanics. And the most obvious explanation is some interaction with electric or magnetic fields of Saturn. The fact that the F ring showed up so brightly in the forward scattering mode suggests that it does indeed have a large population of small particles, and it's small particles that are most responsive to these non-gravitational forces, so that's beginning to make some sense.
Jeff Cuzzy.
We have an enormous data bank here, and we're going to be looking for how do real resonances behave in a disk. That's how I'm going to be treating a lot of this data myself. We're interested in knowing how the planets may have formed from a very similar disk a long time ago by calculating where the resonances are and what kind they are, and looking and seeing this is how the real material behaves at these places. We'll be able to really address this question of how gravitational effects might have been influential in the early solar nebula.
In the days after encounter, something of a consensus began to emerge about conditions on Titan. Gentry Lee and Tobias Owen.
Well, there's no question that the most exciting thing that Voyager has discovered at Saturn, and in my opinion, the most exciting new thing discovered in the solar system, with the possible exception of the Io volcanoes in the last 10 years, is the heavy, dense atmosphere of Titan. For the last 5 to 6 years, every piece of new information that has come in about Titan has been what I would call interest negative or life negative. It looked like the atmosphere wasn't very heavy. It looked like the surface temperature was too cold. And now suddenly, like one bolt out of the blue, we were being told that all the paths that our collective minds were traveling on for the last 5 years were wrong. That in fact, the Titan atmosphere is as thick as almost anyone ever suggested it might be. And more miraculous than that it just abounds in nitrogen. And so, with that kind of a definition and the possibility even being raised of a liquid nitrogen sea on Titan, I feel like we have found a new world in our own solar system, rich and varied, perhaps even as rich and varied as the Earth, with the exception of life.
Titan is an extremely alien world. It's not like Mars or the Moon or even the surface of Venus. We land on Titan, we won't be looking at rocks. We probably won't be looking at impact craters, because all of that stuff will have been buried by the accumulated aerosol, perhaps, if as much of it has come out as we think, and modified, conceivably, by a warm early history in which liquid ammonia, rather than liquid water, was flowing across the surface. So this is a sort of capsule summary of how things may have progressed there. The water would freeze out very early. If it were warm enough for a long enough period of time in the early history of Titan, you'd have some gaseous ammonia, which would be dissociating to make nitrogen, and the remainder would freeze out. Methane doesn't freeze out at these temperatures, and it is evolving and forming these compounds that are being detected in the spectrum, plus the aerosol, which is accumulating on the surface over long periods of time. The reason we find methane and nitrogen in the atmosphere now are that both of them can remain gaseous at these low temperatures. They won't freeze out. And they're heavy enough so that they don't escape. We don't find carbon dioxide because the water, which would supply the oxygen to oxidize the carbon, is frozen solid long ago, and therefore we remain with an atmosphere of methane instead of changing to an atmosphere of carbon dioxide, as, for example, happened on Mars. If our estimates for the production of aerosols on Titan are correct, and a large amount of methane has been used up this way, then we can postulate that the early atmosphere was denser and even warmer, if ammonia was available, than we find today. When the first bit of data came in, it looked as if Titan would be covered, or could be covered, with a global ocean of liquid nitrogen. It now seems that the profile is deviating from this. It's going to be warmer at the surface than you would expect. So what we would expect is that down on the surface of Titan, there will not be a global ocean. There might be a polar lake or something like that, where the temperature is lower of liquid nitrogen. But the rest of the planet would be too warm to have liquid nitrogen on the surface. So you could expect these clouds to form. Clouds of liquid nitrogen should form. Rain could occur, but it'll be like rain that you see over the desert. Namely, you see these trailing wisps of cloud coming down, and it never reaches the ground, except perhaps at the poles. I should mention that in that early atmosphere, ammonia would have served as a very good greenhouse agent to block infrared radiation and keep the atmosphere warm. Today, there seems to be a slight greenhouse effect produced simply by the nitrogen itself. That means we would have had an early atmosphere which was rather similar to the kinds of atmospheres that classically have been postulated for the early Earth, and some very interesting chemistry could have taken place at that time. And that chemistry might well be preserved for us, frozen out on the surface.
The second Voyager spacecraft will reach Saturn in August 1981. and then perhaps cruise on to explore Uranus in 1986 and Neptune in 1989. But Voyager 1 is now leaving the solar system.
I would like to just give you a brief idea of where Voyager 1 is going. We are not shutting it off at all. There are some of us who are very interested in what lies beyond the planets. And of course, Voyager 1 now has been deflected up and out of the plane of the planets very steeply. And sometime in the next decade, probably toward the end of the decade, we would hope that the Voyager 1 spacecraft can leave the influence of the sun, leave the material of the solar system behind, and penetrate into the interstellar medium, where presumably we should be looking at material from other stars for the first time.
There is a particular star which Voyager will come relatively close to, say within 1 to 2 light years. It will approach the star numbered AC79 3888, and it will do this in about 40,000 years. But if you consider very long time, millions of years, for example, it turns out that the motion of Voyager will be in an orbit around the center of the galaxy. And in fact, it will, sometime, a long time in the future, will again come close to the Earth.
By close, Paul Penzo means within several light years. After that, Voyager 1 will continue to make a long orbit around the center of the galaxy, perhaps 4 circuits every billion years, until that distant time when our galaxy itself meets its final fate in the great collapse, the great falling together of all the galaxies that may mark the end of our universe. Or perhaps, if space keeps expanding and doesn't collapse, Voyager 1 will last forever, a tiny ancient relic of those who once launched it. And that would be a nice place to end this program. But there's something else that needs to be said. The Voyagers may be the last of their line, because NASA's program of planetary exploration has fallen on hard times, despite the success of missions like Voyager. Carl Sagan.
In fact, the exploration of the solar system is an extremely powerful affirmation of, among other things, being alive, of wanting to understand where we are and who we are. There are practical benefits. By comparing other worlds with our own, we improve our understanding of both of them. There is a sense of doing something of historical significance that will, as I said before, be remembered centuries and millennia from now. And yet, these comparatively inexpensive and historically significant studies are being choked off because, with one exception, after Voyager, there are no further missions by the United States for the exploration of the solar system.
I just read 2 days ago a very fine article in which the unmanned space program was called the Parthenon of the American civilization. And here's this absolute monument to man's cleverness and to a society on point in an activity that's worthwhile for its entire citizenry, sort of falling into acute desuetude. And it's very, very sad for me. You don't tear apart one of the finest and most creative engineering organizations has ever been put together and believe that you reassemble it on command at some later time. Imagine if you were an extraterrestrial and you've been watching this planet and this solar system for millions and millions of years, and suddenly noted that in this time, in this generation, we reached out for the first time and touched other planets. Imagine your consternation as you watched us land on Mars and send the Voyager spacecraft past three of the gas giants, and there's suddenly nothing. Imagine what you would write. In the second half of the 20th century, this species, Homo sapiens, developed the capability of exploring its own solar system. It then spent a century trying to figure out whether or not to employ that capability.
Voyager at Saturn was recorded at the Jet Propulsion Laboratory of the U.S. National Aeronautics and Space Administration in Pasadena, California. The program was prepared and presented by John Lomberg. Studio production, Max Allen, with Peter Beamish and Matt Wilcott. I'm Russ Germain. We've prepared a poster with color photographs of Saturn and Titan. It's free, and we'd like to send you a copy. Our address is Ideas, CBC Box 500, Station A, Toronto, M5W1E6. That's Ideas, Box 500, Station A, Toronto, M5W1E6, for your free color poster of Saturn and Titan.
CBC Stereo.